So in this video we're discussing the head form of the energy conservation law. We have recently obtained an equation for the energy conservation law for a control volume using the Reynolds transport theorem. Today we're going to write the head form of this equation. What do we mean by the head form for a start? In chapter 3 we have discussed pressure, and we have gave several units of pressure, and one of these was the millimeter Hg, if you remember, and that was a unit in which we describe the pressure in terms of the height of a mercury column. This is called the usage of a head pressure, in which we actually describe the pressure in terms of heights of a fluid rather than the SI units. And we will do the same thing for the energy conservation law. We will arrange it to have terms of height, and we'll call it the head form of the energy conservation law. We basically do that in order to obtain the different terms per unit weight rather than the actual energy terms. So if you remember our energy conservation law that we have obtained using Reynolds transport theorem, it had the following form. So we have obtained the following equation, and basically we had several terms to consider. Of course, this equation was for a steady state. I have removed the time dependence, so this is steady. Otherwise, I would add the d by dt term, and we have also neglected viscous forces. We considered that we have no electromagnetic forces as well, and we considered that we have well-defined inlets and outlets, and that was the equation that we have obtained. On the left-hand side, I have the quantities that I obtained from considering the energy conservation of a system. The first quantity was Q net N dot. This is the net rate of heat that is entering into my control volume. If I have heat that is actually leaving my control volume, then this quantity would simply be a negative. My second quantity is W dot shaft N. This is the power of a turbine or pump. If I have a pump, then W dot is going to be a positive quantity, whereas if I have a turbine in which I'm using the flow of the fluid in order to generate some work, then W dot shaft is going to be negative, indicating that work is actually being done by the fluid, not on the fluid, and thus it's contributing to the output energy, not to the input energy. On the left hand side, I have the quantities related to the input and output energy. So I have here sigma m dot into H plus alpha V squared over 2 plus GZ. Of course, H here is the enthalpy, which is U plus P over rho. It's the internal energy, the specific internal energy, plus P over rho, which is the quantity I obtained from the work done by the pressure difference. And I have here the kinetic energy of my fluid and the potential energy of my fluid. This is over the inlet, and I have the same situation over the outlets. So this was the equation I have obtained. I'm going now to try to obtain a head form for this equation. First of all, to do a small simplification, I'm going to consider one inlet and one outlet. So this way I can get rid of the sums that I have here in my equation. So this will give me basically Q net dot plus W dot shaft N to be equal to m dot into H plus alpha V squared over 2 plus GZ minus m dot into H plus alpha V squared over 2 plus GZ. Now I will always consider my inlet to be 0.1, so that here this would be over 0.1, and my outlet is 0.2 here, so my outlet will be 0.2. Of course, the mass flow rate, because I have a steady flow and I have only one inlet and one outlet, then m1 dot equals m2 dot, and I will name this m dot in my equation. Now I'm going to substitute H by U plus P over rho because I'd like to separate the internal energy from the other quantities. You will see later why, because I'd like to relate it to some energy losses. So this will give me Q dot N plus W shaft N equals M dot into U plus P over rho plus alpha V squared over 2 plus GZ 1 minus M dot into H plus alpha V squared over 2 GZ over 0.2. You can see that my equation now has a bit of a simplified form as compared to the first one. Now, in order to obtain the head form, I'm going to divide by M dot G. This, you will see, is going to give me units of height in my equation rather than units of energy. I'll have Q dot net over M dot G plus W shaft N dot over M dot G equals U over G plus P over rho G plus alpha V squared over 2 G plus Z. 1 minus oh, I forgot to substitute this by U plus P over rho. So this becomes U over G plus P over rho G plus alpha V squared over 2G plus Z over my outlet. You can see how now each term actually has the unit of height, which means I have this head form of my energy equation. I'm going now to rearrange my equation so that I have some inputs on one side and outputs on the other side. So I will actually leave W shaft N over M dot G on one side, plus I will bring the term which contains my outlet to the left-hand side. On the right-hand side, I will still have P over rho G plus alpha V squared over 2G plus Z over my inlet. You can see that Q dot net, which was on the left-hand side, I'm taking it to the right-hand side. And you can see that I have removed the internal energy from the inside of these brackets, so that I should add here one more term, which is U1 minus U2 over G. This is the head form of the energy equation. And you can see that all the terms have units of height. Now I'm going to define a quantity here which will be equal to the sum of these two terms. I will call it the head loss, HL. This is basically going to be the head that will tell me about irreversible processes which will cause some lost energy due to friction. So this term will tell us about the lost energy due to friction. If we have no lost energy, then this term can become zero, and then you will see that this leads to having Q dot net over M dot G equal to U1 minus U2 over G. What does this tell us? Q dot net is now equal to M dot into U1 minus U2. This is telling me that the change in internal energy is only due to heat exchange. This is in the situation where I have no irreversible processes. However, in reality, you will see that we actually have frictional losses for sure, and thus HL will not be zero, and actually you will see that the change in the internal energy will be greater than Q dot net over M dot, which is telling me that the change in the internal energy is greater than the heat exchange. And that makes sense because internal energy changes will arise from other contributions, not just from the heat input or output, especially when we have frictional forces. So here HL is going to be different from zero. So now we can actually rewrite our equation. We will have W dot shaft in over M dot G plus P over rho G plus alpha V squared over 2G plus Z over my output equals P over rho G plus alpha V squared over 2G plus Z over the input plus HL, which is now the head loss due to irreversible processes. The second term I would like to take a look at is this term, which is W dot shaft in. This is basically equal to the input power of pumps or turbines that I have in my control volume. So basically I can actually write this as the sum of W dot of all pumps minus the sum of W dot of all turbines that I have in the control volume. You can see how I put a minus sign for W dot of turbines, and that's because turbines actually give some output work from the energy of the flowing fluid. So this is going to have a negative quantity for the power, indicating that this is an output, not an input energy into the fluid. Usually we have one pump and or one turbine, so I can just write W dot shaft in to be equal to the work done by the one pump that we have minus the work done by the one turbine that we have. So you will see that usually you will have either one of these, so there is no need for me to put the sum. But if I do actually have many pumps, I can always just sum the power of these two pumps and put it in my energy equation. Now, if we actually get back to our equation, we can just substitute this instead of W dot shaft in. However, there is one more thing I want you to consider in our study of the power. So far we were considering W dot, which is the power of the pump itself or the turbine itself that we have in our fluid. However, in this case we were considering ideal pumps and turbines. But in fact, we don't really have ideal pumps and turbines. We have to consider the efficiencies of these devices, and the efficiency is going to limit our output power. So instead of just writing down W dot for the turbine or the pump that we have in our fluid, we need to account for the efficiency. So let's recall our expressions for efficiency. If I have a pump, the efficiency of the pump is going to be equal to the useful power that is going into the fluid over the shaft power that is coming out of my pump. So basically, this is my efficiency. For any pump or engine, the efficiency is defined as the output over the input. And here my output is the useful power that is going into the fluid, whereas my input is the shaft power of the pump itself. And this is usually smaller than 1, right? And now I'm going to define H pump U. This is going to be the useful head supplied by a pump in my control volume. And this will substitute the W dot shaft that I had in my equation. And this head is going to be equal to the efficiency of the pump times W dot of the pump over M dot G. So that was first my shaft term for an ideal pump. Now I have this non-ideal pump with a certain efficiency. So all I have to do is multiply by the efficiency of the pump in order to obtain the actual useful head that is supplied by this pump. Similarly for a turbine, I will define nu for my turbine to be the shaft power output over the power out of my pump. So this is basically the inverse, because in this situation, my input is the work done by the fluid, whereas my output is going to be what I obtain out of this fluid. So I can write now H turbine E. This is going to be 1 over nu turbine W dot turbine over M dot G. And so now I can just rewrite my head form of the energy equation while including for the heads due to the energy associated with the pumps and turbines. And you can see now, in addition to HL, which is the head loss due to reversible processes, we will have H of the pump and H of the turbine to account for the loss energy in generating shaft as well. So now our conservation law becomes H pump U plus P1 over rho G plus alpha V1 squared over 2G plus Z1 equals P2 over rho G plus alpha V2 squared over 2G plus Z2 plus HL plus H of a turbine that I can have in my fluid. You can see how I'm arranging the inputs on one side and the outputs on the other side. So a turbine energy is usually an output energy of my fluid, so I took it to the right hand side. And that's basically the equation that we will be using for the study of the conservation of energy. You will later see that actually this equation will simplify into Bernoulli's law. I think this is clear to you already, because you will see that if I don't have any pump or turbine, just a flowing fluid and no frictions, my equation becomes P1 over rho G plus alpha V1 squared over 2G plus Z1 equals P2 over rho G plus alpha V2 squared over 2G plus Z2. And this is basically Bernoulli's equation.